Welcome to the session on parallelism. We have 4 very interesting papers, and we're going to start with, make sure I get the title correct, Pipelines and Beyond, Graph Types for ADTs with Futures, and Francis Rinaldi will give the presentation.
Thank you, John. Hope everyone's doing well. I'm going to be presenting our new work on graph types. I worked on this while researching under Stefan Muller. It was also done in collaboration with June Wunder and Arthur Azevedo de Amorim. So I'll start with a quick overview on graph types, which were introduced a couple years ago by my advisor. A graph type is a type that represents the dependency graph of a program. So here at the bottom are some examples of dependency graphs, also known as cost graphs or computation graphs. And they describe the parallel structure of a program's execution. The left one says that there's no parallelism. The right one's saying that B and C were performed in parallel. Now, because these graph types describe these graphs, they're able to represent the parallel structure of the program. And one of the boons of graph types is that they're able to do this statically, as opposed to dynamically. Now, one can imagine that these dependency graphs can change quite a bit due to control flow within the program. And this is another great feature of graph types. They're able to represent all possible dependency graphs for a given program. Now, graph types are derived using a graph type system, where we have a typing judgment that assigns both a standard type tau as well as a graph type G to the program. And one of the key properties of a graph type system is that it is sound, which we define as meaning that if we assign a graph type to a program and the program evaluates in a way that corresponds to a dependency graph little g, then the dependency graph is going to be in the set of graphs represented by that graph type. Now, graph types are useful for static analysis. We believe that they can be looked at by a machine to do things such as detection of parallel bugs or improvements when scheduling. But one of the main motivating things we've been providing is a tool for visualizing these graph types. So the idea here is that a programmer, while programming, can look at the graph type of their program and analyze and assess the parallelism of their program. Now that I've explained how graph types are awesome, let me talk about an example here where we implement graph types. We have a program, it executes A, and then it creates a future. What a future does, for those who don't know, it spawns a thread that will execute whatever code is passed into it. Back on the main thread, we execute C while the future is executing B, and then we touch the thread to sync the future with the main thread. And here's the dependency graph of this program. The black arrows represent the main thread, the red arrow is the future, and the blue arrow is syncing the future. Now, here in the box is the graph type of this program. This circle plus here indicates sequential composition. And what this graph type is saying is that the program will do A, and then this part in red, and then C, and then finally this part in blue. Now, you might be able to tell from the colors, the part in red is indicating that a future is being spawned. That's what's indicated by the downwards left arrow, syntactically. To the left of the arrow, this B is saying that the future executes B, and then to the right of the arrow, this graph type, to the right of this arrow is what we call a vertex. And this vertex is very special. It is a unique reference that is uniquely associated with that specific feature. And we have this for use within the graph type. Now, intuitively, this vertex is going to be the name of the last node that is represented by the feature in the dependency graph. And I've updated the dependency graph to show that here. Now, back in the blue here, this downwards right arrow indicates that a feature is being touched. And the vertex to the left indicates which feature is being touched. Because the U in the red and the U in the blue are the same, they're the same vertex, the graph type knows that the feature being touched in blue is the same as the feature being spawned in red. Now, when assigning these vertices, when we spawn a feature, the graph type will just give it a new vertex. But how does the graph type know which vertex to give it when we touch a feature? It looks at the type of the feature to do that. So here we have roughly our typing rule for a feature. When we construct a feature, we assign it a fresh vertex U, and then store that vertex in the type of the feature. Now, let's say this feature gets passed around and touched later on in the program. The graph type is able to look at the type of that feature to determine which vertex to use, so that it knows specifically which feature is being touched. Now, as a consequence of assigning each feature a unique vertex and us storing that vertex in the type, this has the consequence that every unique feature has a unique type that will differ at the very least in the vertex. And this can cause some problems when it comes to data structures containing futures. Here we have a list of 2 futures. Without any vertices, this would just be typed as an int future list. But when we add vertices, all of a sudden, these 2 futures have 2 different types. Now, this is a problem because we can no longer type this list in a type system that only supports homogeneous data structures, such as the previous graph type system. Now, I provide a motivating example here of a parallel algorithm introduced by Blalock and Reed-Miller in 1997. And this is an algorithm that uses a data structure containing futures, so it cannot be used in conjunction with graph types. At the top here, we have a type definition for a pipeline data structure. A pipeline will either be empty or will have an element followed by a feature that constructs the rest of the pipeline. And a data structure of this type is useful because early elements of the pipeline can be used while later elements of the pipeline are still being constructed. We also have a produce function, which will produce an integer pipeline of length n. We have a consume function, which will consume an integer pipeline of length n. Sorry, not of length n, just of any length. It will sum up its elements. At the top level, we produce a pipeline of length n, and then we consume it. Now, again, the problem here, we have an algorithm that uses a data structure containing futures, and as a result, we're not able to type it, and we're not able to graph type check it. So yeah, this is where our new work with vertex structures comes in. A vertex structure solves this problem. A vertex structure is also vertex structure is a code data structure of vertices, and it is used by the type system to map vertices onto elements of a data structure containing futures. And it accomplishes this by having the vertex structure representing the data structure structurally mimicking that data structure. As an example here, we have a list of 2 futures on the bottom. Right above it, we have its corresponding vertex structure, where we map the nth vertex of the vertex structure to the nth future in the list of futures. And I'll touch in a moment as to why this list is infinite, the list of vertices. Contributions, we introduced lambda g mu, which is a new parallel calculus that introduces the second iteration of our graph type system. It is notable because it uses vertex structures to solve the aforementioned problem. We have a soundness result for lambda g mu, and we have a prototype implementation of vertex structure inference. What do I mean by this? We're going to be adding vertex structures to the code itself. And our general philosophy is that we do not want the programmers to have to worry about adding these vertex structures. We want graph types to be as easy as possible to use. And so we have a program that will automatically add these vertex structures to the code. Finally, we have a formulation for the key part, for a key part of this inference algorithm, which I'll touch upon later. And I'll talk about vertex structure types first, because frankly, they're more interesting than the vertex structures themselves. Vertex structure type curly U can either be a type of a vertex, which is the black diamond, or it can be a product type or a co-recursive type. Now, why do we have these type constructors? It's because they allow us to describe the type of any infinite tree of vertices. And that's important because that means that every data structure can be represented by a vertex structure that is well typed. I'll give examples of this correspondence between a data structure and the type of the vertex structure that should represent it. As we know, a feature is going to be represented by a single vertex, so the type of that vertex structure representing it is going to be the type of a vertex. For a pair of futures, we're going to need a pair of vertices to do that. If we have a list of futures, we have a stream of vertices. Now, the reason we have an infinite amount of vertices here is because prior to runtime, remember, this is all being done statically. So prior to runtime, we don't know how long this list is going to be. But if we have an infinite amount of vertices, we'll definitely have enough vertices to represent that list. Finally, I'll talk about the syntax of the vertex structures themselves, capital U. So prior to this, I've been using the little u to represent the vertex. From here on out, it's going to represent a vertex structure variable. And these vertex structures can also be pairs or projections. Now, I'll be going through the motivating example from earlier, adding vertex structures to the code piece by piece, to show 2 things. One, how we can use vertex structures to map vertices onto data structures containing futures. And 2, how after all these additions, we're able to now assign both a type and a graph type to this program in a graph type system. So first step is going to be the type of the pipeline data structure itself. What we do is we index the pipeline type with a vertex structure. And this vertex structure is going to be the one representing this pipeline. Now, why do we choose vertex stream? It's because the pipeline type has 1 feature per recursive layer. And we want to mirror that in the type of the vertex structure, which is going to be this vertex stream shown at the bottom. And then we also, you'll see this pattern a lot, where we use the head of the stream to reference the future, and then we use the rest of we pass the rest of the stream into the recursive instance. Next up we're going to be adding is the produce function. Now we parameterize this function with the vertex structure that is going to represent the pipeline returned by the produce function. And see this pattern again. We pass the head of the stream to the future and the rest of the stream to the recursive instance. And remember, we want to be able to type this function. So I'm going to need to talk about how we change the function type within a graph type system. There's two new components. We had a vertex structure parameter, which matches the one in the function. And then we have the graph type of the function body. Now, when we declare a function, we don't actually execute it. So the graph type of a function declaration is just going to be nothing. But we still want to be able to capture and keep track of the graph type of the function body. So we annotate that in the type. And with that, before we delving into the graph type stuff, I'm going to give it the partial type of the produce function here. So we can see again that we have the parameter in the type matches the one in the code. And then recall that we're using this vertex structure to represent the pipeline that is returned by this function. So we index the inputted vertex structure into the pipeline type that is returned. Now I'm going to describe the body of the graph type. And to do that, we're going to need to talk about the syntax of these graph types. So this black dot indicates arbitrary sequential execution. Now, remember, these graph types are meant to represent the parallel structure of the program. So if we have just a bunch of sequential code, we can just abstract that away into this black dot. We also have, from what we saw from earlier, the sequential composition. We have a disjunction operator to indicate that the graph type is either this one or that one. And we have a recursive graph type. Now, these are the future spawn and future touch that we saw earlier. Instead of using vertices, we now have vertex structures. But this is just a syntactic difference. We enforce within the type system that these vertex structures will be vertices. Finally, we have a graph type function, which will take in a vertex structure. And this function is useful in the context of a recursive binding, where we can pass different layers of the vertex structure into different recursive layers of the graph type. And we can see this in action here, where we are able to give now the graph type of the function body. This graph type is saying that the function will take in a vertex structure parameter of type vstream, and then it will either do this black dot, which indicates, corresponds to the fnil branch of the program, or it will spawn a feature using the head of the stream again, and then inside that feature, we have a recursive instance that uses the rest of the stream. With that, we've seen this all before. This is the type and the graph type of produce in one slide. So next up, we're going to be adding vertex structures to the consume function. This is going to be very, very, very similar to the produce function. So the only thing of note is that the parameter is going to be used to represent the inputted pipeline instead of the outputted pipeline. So I'll just get back this slide. Just trust me, it's all good. Finally, we're going to be adding vertex structures to the top level of the program. So I've been talking about how to construct these vertex structures. That is done using this new expression, which will construct a vertex structure of the given type, and then bind it to the variable here. So here, we create a vertex structure of type vstream, bind it to the variable. The reason we do this is to create a vertex structure that represents the pipeline returned by produce, and therefore it's also going to represent the pipeline that is given to consume. So we pass that vertex structure to both functions. Finally, with that, we're able to assign both a type and a graph type to this program. And the type isn't very interesting, but the graph type tells a different story. So here, the graph type saying the program will create a vertex structure of type vstream, then do produce, then do consume, and we pass that vertex structure to both of these functions. And that allows the graph type to know that the nth feature being touched in consume is the nth feature being spawned in produce. Now, I haven't talked at all about how to add these vertex structures to the code, because that's outside the scope of the presentation. But we do have an implementation that does just that for a subset of OCaml extended with features. And not only that, but this will also type check and graph type check this program. And it also comes with a visualization, as I said from earlier, which will visualize the graph type that you get from this implementation. So this is the visualization for this example. I'm not going to go over it for time. But yeah, takeaways for this presentation. We were previously unable to graph type check algorithms that contain data structures with the features. We introduced vertex structures to solve this problem by having the type system map vertices onto the data structures. And this allows graph types to be more expressive and more applicable. More in the paper, probably the most challenging thing I haven't talked about is that we need to treat vertices finely when it comes to spawning features, because it would be a problem if a vertex was used to reference more than one feature. We also have a soundness result. Most interesting thing here is that we need to describe what it means for a graph type to represent a graph. And as I said, we have a formulation for a key part of the inference algorithm. The important part of here is that we're able to now prove that every data structure can be represented by a corresponding vertex structure. And with that, I'd happy to take any questions.
So we should have plenty of time for questions. There's microphone, I guess there's.
So if you go back to the work by Belllock back in the 90s, it's very easy to assign the type if you're, to this program with futures.
Just a little bit. Yeah.
So what exactly are you going to do then with the graph types, which are very complicated on top of that? Because this is already safe, right?
Sorry?
This program that you have there is a perfectly well-typed
Yeah,
program.
yeah.
Futures will execute okay. So what are you going to do with the graph types? I mean, what are they used for?
Yeah, so these graph types are not used for verification. They're used as a tool for analysis. You might recall I said earlier, the idea is that we can have probably a program look at these graph types to analyze the parallel structure. And possible applications of that is detection of parallel bugs or improving performance. And again, we're able to use this graph type to make a visualization of the program, of the general parallel structure of the program.
Just to follow up, you have a compiler then that uses that information for optimization, or is it just is that future work?
No, that's I believe that's future work, but it's something we theorize is possible.
Thank you, very interesting. I have got a question about when the future, I think you use the term joins, and it seems to me that the future joins, when it joins is determined by the lexical scope. There are approaches or variations where you have got a handle and the future joins when you read the future. And then it seems to me, I don't see how you would be, whether you are able to handle it and whether you can extend your system to handle this pattern of the future joining dynamically because you are reading from it.
I'm unsure. Sorry to have. Okay.
Yeah, but the touch, how can you know which future you are touching? If there is a variable on the future and you are passing it around or it's in the heap, you don't know when you are touching it and which one you are touching.
Yeah, so that's what why the vertex is included in the type of the future. So when you touch fnums there, at the type of fnums will include the information about what future it is.
Okay, so I think we have time for one question from Discord, and you should. So, question: how would you represent the vertex structure of a function type A arrow future B?
Well, I guess a function type is not a data structure. So I don't believe it would have a corresponding vertex structure.
Okay, so let me ask a different question from Discord. So how do you ensure the vertex names are in a vertex structure are distinct, or is distinctness not required?
Yeah, so what do? When we create a new vertex structure, we say that all the names in that vertex structure are fresh, and we don't actually evaluate this program with the vertex structures, but in evaluating it in the paper, what we do is we basically say, we lazily generate these vertices, and we're able to just keep track of names we previously used.
Thank you.